Hello, today I explain about the review of physics electronic continually from the last time. First, the part 3 is about doping. When the silicon semiconductor is doped by uh, donor dopant like this 15 group element phosphorus, the covalent bonding is occurred. When you see this picture, the free electron is occur and donor dopant is ionized by plus because phosphorus has one more electron than silicon, so the free electron is occurred, uh, and the number of donor dopant is equal to the number of electron carrier, so the concentration is also occur. Next is acceptor doping. Uh, it is also the when the silicon semiconductor is doped by uh, the 13 group element like boron, the covalent bonding is occur. And if you see this picture, the whole carrier is occur, and also uh, the acceptor dopant is ionized by minus because this dopant has one less electron than silicon. So the whole carrier is occurred. Also, the dopant concentration is equal to the whole carrier concentration. And next is about the carrier concentration. Uh, it, Before we explain about the carrier concentration, uh, we know about the density of state function and Dirac, Fermi-Dirac probability function. Density of state function means that the number of states that electron can occupy, and Fermi-Dirac probability function is about that the energy level that uh, electron can go at specific temperature. So you can see this temperature and energy level. So the carrier concentration is simply the product of density of state function and Fermi-Dirac probability function. Next, I explain about the PN diode. First, I explain about equilibrium state. Uh, Before I explain it, I explain about the Fermi level. Fermi level is the energy level that the electron existence probability uh, is 50%. So if you see this picture, when the N-type and P-type semiconductor is contact, the hole carrier and electron carrier is recombinated. So in this region, there are uh, almost no carrier. Uh, in this area, in this region, there are hardly electron. So we call this region a depletion region. Also, in this region, there are just ionization dopant like uh, like phosphorus and boron. After the contact, the carrier has no move, so the Fermi level is constant at n-type and p-type junction. So next, when you can see this region, the depletion region in n-type is bigger than this p-type p-type depletion region, because the p-type semiconductor is more doped than n-type. So at this small region, at this uh, small region, there are many there are many uh, dopant than the n-type. So if more and more doping area has the small depletion region, and this dopant ionization dopant occur the electron field. If you electron field if the electron field is differentiated, if you uh, if the electron field is differentiated by Poisson equation, you can get the total quantity uh, of electron charge. If you see this graph, if you see this Q and distance graph, you can see this, and also this area and the n-type depletion area and p-type depletion area is same, because the number of carrier is at the depleted the number of carrier that depleted is same. Next, if we integral this total quantity, you can see this electron field. When the at this boundary of depletion region, the electron field is max. Next, if we also integral of this electric field, we can get the voltage and distance graph about the potential energy. Next, we use this graph. We drawing the picture of energy band diagram of PN junction. So you can see this Fermi level is constant. Next, if we applying the forward bias at this PN junction, the energy barrier is low because the depletion region is smaller. Next, if we apply the reverse bias to the PN junction, the depletion is large and the electron barrier is large, so the current can't flow easily. At the reverse bias, some problem is occurred. Uh, uh, the uh, the one problem is avalanche. When the summer energy is applied, when the electron get some thermal energy than the electron generation. And the electron flow by the inner electron field or other things. And this one, and the other electron is scattered by this electron that get energy. So this this generation and scattering again and again, the current is flow very big, very large. So this is called avalanche. And if we apply the reverse bias very large, then this energy band gap at deflation region is very thin. So the electron can through the energy band gap, and this is also occur the current. Next part 5 is MOSFET. You can see state. This state is accumulation. The MOSFET is metal oxide semiconductor capacitor. So when you apply the voltage gate voltage lower than flippant voltage at this, the Hall carrier at P substrate is pulled by this negative gate voltage. So at the accumulation, the plus channel is occurred. And next is depletion. When you apply the gate voltage larger than flatband voltage and lower than threshold voltage, the plus voltage push the Hall carrier, and at the surface, the depletion region is occurred by dopant, ionization dopant. Next state is inversion. When you apply the gate voltage larger than threshold voltage, the plus gate voltage pull the electron carrier from to the surface of depletion region. So the depletion region is disappear, and minus electron n-type channel is occurred. So when you see this capacitance and gate voltage graph, when the accumulation state, the C total is equal to C oxide, capacitance of oxide. And next, depletion and weak inversion, the C total is low, because when the depletion region occur, the capacitance is plus, like this, capacitance of oxide plus capacitance of depletion. So total capacitance is lower. And at the high frequency, if the high frequency, this frequency is interrupt the electron, so the n-type channel don't occur. So the depletion region is maintained. But when we apply the low frequency, anti-channel can occur. So at the inversion, C total equal to oxide capacitance. Next, I explain about the energy band diagram of MOSFET at inversion state. If you see it, if you see this work function and this potential energy difference, this work function is mean the vacuum energy minus the Fermi level energy. So if we subtract the work function of gate and substrate the work function of substrate, this means that the how much is it bent, and this energy level, this subtract means that the quantity, product, and pi f, and also this pi s and pi ox is also this about the bending. And we use this parameter, we can get the gate voltage and threshold voltage. The gate voltage is equal flat band voltage plus oxide voltage plus pi s. Flat band voltage is equal to this subtract of work function, because before I explain, this one means that how much is it bent. So if we flat this bending, we apply gate voltage uh, about this value. So the flat band voltage is equal to this substrate, and oxide voltage is equal to this the total quantity of semiconductor and capacitance. Because voltage, oxide voltage means that how much oxide is bending. So you can get this voltage by capacitance equation. Uh, total quantity of charge is equal to capacitance product voltage. And next one is pi s. Pi s means that how much substrate is bending. So when the gate voltage is equal to threshold voltage, that is strong invasion occurs, that this substrate potential energy difference is equal to this two subtract of intrinsic energy and Fermi level energy. Next, part 6 is about transistor. This transistor meaning is that when you apply the gate voltage to this transistor, you can control this channel conductivity by transforming resistor, and transistor act as switch and amplifier. Next, I explain about the MOSFET, that the one type of transistor. Before I explain about enhancement mode, you can see this picture. This picture is similar like MOSFET. Uh, MOSFET is just adding the source and drain by n type doping from the MOSFET. Uh, so if you see this graph, log scale drain current and voltage gate graph, uh, if the voltage gate is less than threshold voltage, this region called as linear or triode region, and on the other hand, saturation region. And at this graph, the channel and the enhancement mode means that if the channel is occurred when the gate voltage is larger than threshold voltage. And next, you can see this triode region current and saturation region current. Next, if you see this graph, gate voltage and channel length, if at the channel is exist, the and also the drain voltage is equal to overdrive voltage. The overdrive voltage is gate voltage minus threshold voltage. At this, the pinch off is occur. This is pinch off. The edge of channel is exist at the surface of drain. So when you apply the drain voltage larger and larger, the channel length is smaller. So the electron can't pass through the channel, can't pass through the channel easily. So the current is saturation. But in the real, the channel length is small. The channel length transform is uh, at this but in real world at this situation the current is not saturation because this channel length uh, affect the current. This problem is called as short channel effect. Next one is depletion mode. It is simple. Uh, it is if you don't apply the gate voltage, uh, even if you don't apply gate voltage, the channel is exist at first because threshold voltage is minus. And the channel, if the channel is n-type, that MOSFET is called n-type MOSFET, and p-type channel that called as p-type MOSFET. And if you make the CMOS by the MOSFET and PMOSFET, you can make the CMOS inverter gate, and you can use this make the logic gate. So and next, there are other transistors, uh, silicon on insulator and FinFET, and these ones is made for reducing short channel effect. Next part 8 is memory. There are two types of volatile and non-volatile. Uh, Volatile is that when you if you turn off the power, the storage is the data store the storage data is disappeared. And non-volatile means that uh, even if you uh, turn off the power, the storage data is maintained. Next, I explain about the SRAM, about the RAM, about random access memory. SRAM is the static random access memory. This one is this one has 6 transistors that 2 transfer transistor this uh, these two and 4 transistor at this latch at this latch uh, at this latch uh, this latch is this latch has 2 CMOS. So SRAM is very fast by this latch structure, and power dissipation is lower. But the this SRAM size is big, so the device integration is lower. SRAM is using as CPU. Next one is DRAM. DRAM has one transistor and one capacitor. Because of the capacitor, DRAM is slower than SRAM, and the power dissipation is bigger than SRAM because capacitor capacitor uh, if we want to check the data you need refresh at capacitor by power, so power dissipation is higher. DRAM is using at computer main memory. Next one is flash memory. This one is non-volatile type. This one is similar to MOSFET, but the floating gate and the buried oxide is adding. So when you positive gate voltage, if you apply the positive voltage, the electron carrier is trapped in this floating gate. This is called as write. And if you want to this data erase, you apply the negative gate voltage, then the electron is get out from this floating gate. If you want to read at this graph, if you apply the read voltage, when you apply the read voltage, if the current is small, that is in the floating gates there are no electron. this one is zero data. And if you I explain again. If you apply the lead voltage, if the current is very small, that means the data is right, because the threshold voltage is bigger because of the floating gate has because of the trapped electron. So that is one data. And if you apply the lead voltage, the if the current is very big, then there are no trapped electron in floating gate. That's all. Thank you for listening.